Hoi-Lai Yu from Academia Sinica to give the theory seminar. Well, Hoi-Lai and I never overlapped, and he just told me until 1986. But we did have, some overlap in space. So Professor Yu did his undergrad, in fact, at Normal University, next door to us here. But he's originally from Hong Kong. Then he went to University of Pittsburgh and received his PhD in 1982. Now, my encounter or overlap with him is that I also worked with Ray Willie, a late professor there, when I went to Pittsburgh as a postdoc in '85. And so we had some topic overlaps already during that space-time period. So after Pittsburgh, Professor Yu went to Southampton in England as a postdoc, and then came back to Taiwan in '85 to Zhongyuan Christian University. And in '87, he moved to Academia Sinica and stayed there until now and becoming a 研究员, a research fellow there. As far as I know, Hoi-Lai is really a very special person. Not just that I commented to him that he keeps really well. You see, he controls time, right? But I observed that Professor Yu follows his interest. So that's a very special kind of person. So his interest has varied, and since a few years ago, I don't know, I can't recall how long, he got interested in loop gravity. But he just told me that this is beyond loop gravity. So I think it's a great big title, something that attracted us to physics, and I leave the floor to you, Hoi-Lai.
Yeah, thank George for the nice introduction. Well, actually, you guys will be happy because I have only 16 pages and 2 of them are pictures, so that means I have only 13 pages. So that means I want to make clear what I'm going to talk. And let me tell you a little bit history of my academic career. I went to Pittsburgh because of there's a famous professor called Ted Newman. Maybe people know that there's a so-called Newman-Penrose solution for black holes, and that was a big group. But then when I reached Pittsburgh, then I was a little bit disappointed because it's too big. And then I get very small chance to talk to Professor Newman. And then I changed into particle physics. Only maybe about 10 years ago, I come back to, well, I'm old enough. I think I should do something more significant, put this way. That I want to change, at least you see. I want to change the paradigm of physics thinking, in particular the thinking of general relativity. Okay, let me begin. Okay. Well, this is a famous drawing of Wittgenstein. Depends on how you interpret. Sometimes it looks like rabbit, sometimes it looks like a duck. So Hegel said that things which looks different are really the same. Wittgenstein doesn't agree. He said that things which look the same are really different. Today I refer to general relativity when both theory will have the same equation as Einstein's equation. Does that mean that the theory, that means both theory will give the same physical content as Einstein's GR if they have the same equation of motion? Would that mean that these two theories are the same or not? That is something I want to clarify today. And that involves the significance of time. Okay, let's begin with some fundamental facts and observations. first of all, when people say x and t are of equal footing in relativity, what does that mean? Actually, this is a meaningless statement, because I think you guys particle physics, or at least you study field theory, you know that in field theory, the fundamental objects are field operators. X and t are just labeled, integrated out. For your action, you integrate out x and t, so there's no physical meaning. So all physics should be determined by the fields, in this case, by the metric fields. Or the metric field is a simple generalization of Euclidean spacetime to a more sophisticated spacetime that are dictated by these metrics. So actually, I should change this. Actually, that means x and t label is only a kinematic statement. That doesn't dictate the dynamic rule. The dynamical rule. Okay. The dynamical rules actually is dictated by the field operators or by the Hamiltonian of the system. Now, another fact that you can, I think everybody agrees, that you can travel back and forth in space. You can walk back and forth in space, but no way you can go back in time. So how can time and space be equal footing? Also, that means that 2 and 3 actually are correlated. T has causality relation, or causal ordering. That means if TA is greater than TB, and if T and TB are within the same timeline cone, that it means this ordering cannot be reversed. Sorry, it should be reversed. Instead, will be shared by coordinate transformation. Now, the fourth, you always heard that, have a wrong impression that Schrödinger equation is a non-relativistic equation. Well, why people have this impression? Because on the left hand side, d dt psi is first order in time. On the left hand side is h psi bar. Well, h has p square, which is quadratic in momentum, quadratic in space. So you say people begin to say that okay, Schrödinger equation actually is a non-relativistic equation. Actually, this is wrong. Actually, from the canonical point of view, I'll come back to this. Actually, Schrödinger equation is a background independent equation. That means it applies both relativistically and non-relativistically, and also independent of what type of space-time background you're in, whether you're in de Sitter space-time background or in Minkowski space-time. Schrödinger equation is always working. Then actually, Schrödinger equation is the building block. It's the building block of the whole field theory, where one can, from that, you integrate the equation, you can get the unitary evolution operator, and get the Heisenberg picture. Picture. Okay. Now, the deep question is, there's a time involved in Schrödinger equation, d dt. What is that d dt? How do you determine that? Then the next question is, what determines if I give you a space-time manifold that carries time? I mean, what character of that manifold carries time? And then suppose if a manifold do not carry time, or you do not have a space-time, then how can you have a sense of ordering the events? Have a sense of also we call it causality. How do we? I mean, if you don't have time, how can you order? I mean, how can you do a causal order without time? How can you do that? And this is one of the major problem in the problem of time in general relativity. And also, why people didn't make, okay, there's three reasons why general relativity actually get very little breakthrough, not like particle and field. get a huge momentum after 60s because of standard model. Actually, after 1955, general relativity doesn't get much momentum. Actually, doesn't really develop because people has been asked the wrong question first. They ask what are the general solution and the relation with general coordinate covariance. This is a wrong question to ask. This is useless question, and for 100 years this question doesn't bring any deeper physics into the physics of general relativity, and actually drag back the development of drag back the development of general relativity a lot until when computer simulation become more popular, people begin to ask how to, given a arbitrary initial value data, how to evolve it. Then people begin to realize, I mean, the physics is coming from this question, not from the general solution of general relativity. So that means in the past 100 years, thousands of papers on black hole was published. That means all those papers are useless in gaining better understanding of general relativity. I'm not going to say Hawking radiation is useless. I'm going to say that all these thousands of papers working on black hole and those coordinate transformation are useless in gaining a better understanding of general relativity. Okay. I'm not going to say that. Oh, well, they discovered thermal radiation. That is the extra part of general relativity. It does not belong to general relativity. What I'm saying is, those are particular solutions. Doesn't help anybody to get a deeper understanding of what is the physics behind general relativity. Okay, finally, one of the difficult questions I was asked 30 years ago by Professor Tu when I was a postdoc in Southampton is why the world is gauge. And then I try to answer, well, if you have a quantum theory of gravity, then you have to answer this question, I mean, automatically. And then I'll give an answer to this later on.
Will you comment on singularity later
on? Depends on my time. Okay.
So therefore I asked the question here because black hole Hawking radiation is a consequence by trying to incorporate quantum behavior. Okay, but general relativity and the issue of black hole illustrates the issue that within general relativity it brings in the problem of singularity, right? So when you say time ordering this and that, but even those questions break down at the singularity. So therefore, whether there is a singularity has bothered a lot of people.
Okay, first of all, the proof of singularity by Stephen Hawking and Penrose in early 60s was not by field theoretical method. They used the Van Choudhury equation, which investigate a concurrent of light wave. And then prove that this concurrent of light wave to end up as at least we have two points that they will all come together. That's how they prove the singularity. So then the deep question to ask: how about if I'm the law? If I build a world without light wave, would that world be self-consistent? So I think people make a mistake. People make a mistake that they're making the light cone so fundamental. Light cone actually is coming from U1. U1 is not even a fundamental symmetry. So why should light cone be so important? I think why light cone be so important because of history, because people discover Lorentz symmetry, and Einstein incorrectly tried to gauge Lorentz symmetry, and so they make the light cone so special. And for example, given any for Minkowski scale, we have isometry, namely Poincare symmetry. Therefore, we have boost. We have Lorentz invariance. Imagine I have a spacetime like this, any shape. How can this spacetime have a Lorentz boost symmetry? There's no way. You understand my question? I mean, for example, general relativity, suppose you solve your genus and solve the highly nonlinear equation and get a general solution for general relativity, and the space, the most general space-time is something like this. There's no isometry at all. Right? That means there's no point-gradient symmetry at all. Point-gradient symmetry is not fundamental. It's an outcome of solution of, it's an outcome of Minkowski space. That means it's an outcome of solution of Einstein equation. So Nycombe is not a big deal. So in that sense, but there's still possibility of singularity that I'll come back to later on. Okay. Now, first of all, we know that the world is gauge. So we would like to first ask the fundamental question, whether general relativity or the theory dictate gravitation is a theory being gauged. Now, so I try to differentiate what is gauge and what is not gauge. What is gauge transformation? For example, in QED, you do a gauge transformation, the variation of gauge, the variation of the vector potential is just the derivative of the gauge parameter lambda. And more important is, both lambda and A and the comparison of A are written in the same coordinate system reference. This is important. For gauge theory, the variation, you compare two fields at 2 points, the two different field configuration at the same point. Okay, this is the character of gauge theory. But now, you see, under general coordinate covariance, that means that you change x, given you a coordinate, you can always make a new coordinate x pi by building this function, and then we know that the metric tensor is the metric field is a tensor, so it transforms according to this transformation law. Well, then if you subtract this, if you subtract the right hand side from the left, the right hand side from the left hand side, that is nothing. Oh, sorry.
No, it's not your problem. It's the system's problem.
Okay, so okay, good. So that means delta G cannot be made in the same point, cannot be made like a gauge theory. But however, if the transformational coordinate is infinitesimal transformation, for example, x mu transforming to x pi, which is just x mu plus some small vector field mu. Then you can expand using this formula, plug it into this formula. Then you can write down a g pi mu nu x pi equal to this x mu plus this derivative. Now, then afterwards you can do a Taylor expansion on x pi is equal to x plus some vector field, some small vector field c mu. So you do a Taylor expansion and make this g pi x pi into g pi plus this derivative. And this means that the derivative of g pi with respect to x pi has to evaluate at x pi equal to x. Then you can see that the diffeomorphism gauge transformation is a comparison of two gauge configurations at the same point. That means under diffeomorphism, small gauge transformation, the metric tensor really looks like a gauge transformation. So actually, this has been stressed by Peter Berman, who is actually he is an assistant of Einstein in Silicon. I mean, back in the 50s. He has stressed this point. I mean, the general coordinate covariant group is too big. The correct group, the group we can understand actually is the diffeomorphism group, which is that means that the difference in gauge is developed by has to be different in gauge configuration has to be compared at some point. and just looks like QED, except I use Lie derivative because of curved spacetime. This is just d mu. In fact, spacetime this just we reduce to d mu c mu nu. So it's exactly like QED. So under diffeomorphism, the metric tensor it transform really transform like a case configuration. So now once you confirm that you can actually make general coordinate transformation as a kind of gauge transformation, then the next question to ask is, because we have only field operator x, y, z as coordinate, what are the field operators that generate this transformation? That's the next question to ask. Given you, okay, this is a gauge theory, and then you have to ask, what a corresponding operator, field operator that generates this gauge transformation. For example, in QED, it's the Gauss law. Deep dot EU0 is the generator that generates the photon field transformation. That delta mu, that means that delta A mu is equal to the Poisson bracket between A and the Gauss law field operator. So Dirac, then it comes Dirac's conjecture. Well, you can see the superiority of Dirac. Because when he made this conjecture, gauge theory, the idea of modern gauge theory is not exist yet. But however, he still make the guess and then get the right guess. He's saying that knowing all the first class constraints is sufficient to derive all the gauge transformation in the theory. And the gauge transformation of fields of first class, gauge transformation of fields is generated by first class constraint G, actually with the Poisson bracket. It's a simple formula, just like QED. For delta A is equal to the Poisson bracket between the Gauss law and the gauge connection A. Now, if you are not familiar with canonical formalism, you may find first class constraint is a very mysterious object. However, well, you just compare with QED. In QED, the corresponding first class constraint is the Gauss law that implement charge conservation in QED. That is the law that generates transformation. And so we have to ask, what are the field operators, what are the corresponding Gauss law in general relativity? Amazingly, the corresponding Hamiltonian and momentum constraint for GR was only worked out almost 50 years after its birth by Dirac. Now, general relativity, the field equation of Einstein was published on November 25th, 1915. And Hilbert's paper was about 2 weeks earlier. So, and Dirac's paper was published around 1958. So it's almost 50 years. That means, well, a high-power mathematician, high-power physicist, one of the most high-power calculator, spent almost 10 years to calculate the Hamiltonian and momentum constraint for GR. So I doubt it. When the string people claim their theory cover gravity and actually give a correct quantization of quantum gravity, I think this must be overstatement. Because without knowing the Hamiltonian and momentum constraint, there's no way to understand what happened in general relativity. After working out the momentum and Hamiltonian constraint, Dirac concluded space-time covariant cannot be a symmetry of general relativity. Okay, let me switch. Just try to give you some confidence. And let me here. This is Relativity 58 paper by Dirac. He said this in 3 times, in abstract and in one of the sections, and also in the conclusion, that this simplification can be achieved only at the expense of abundant 4-dimensional symmetry. That means 4 covariant of space-time. This is the first space appear in the abstract, also in the conclusion. Also in conclusion, he said that one side of tangent, okay, anyway. He said that it can be obtained at expense of giving up 4-dimensional symmetry. And so here, if expressed in the simplest form, force 1 to abandon the 4-dimensional symmetry of space-time. So we are actually, what I'm saying is, we are not the first people, we are not the first group of people to call for an abundance of 4 covariant. Actually, Dirac and then John Wheeler, they stress again, once again, that one have to abandon 4 coordinate covariance. But however, Einstein is a hero, so not too many people want to override the decision of a hero. Okay. Now, let me introduce you a simple manipulation of general relativity, but one of the most significant development in understanding towards the understanding of general relativity, namely the ADM of 3+1 decomposition. But however, this decomposition actually some people say that they clarify the nature of general relativity actually from our point of view then actually more confusion to the field. So the idea is simple. Idea is given any 4-dimensional space-time, say 4 manifold, then you can slide this 4-dimensional manifold into a 3+1. You can slide it into a 3 manifold, and then stack up this 3 manifold to form the 4 manifold. This is called 3+1 decomposition. Why we have to do that? Because we want, for example, you have one slide, and then I try to evolve this line by Hamiltonian to the next point. I have a slide of space-time at t equal to t, and then I want to evolve this space-time to t plus t dt using an Hamiltonian. So that means I can, for this type of geometry, that means I can first evolve for this point A, will finally move to point C under this evolution. Then, but however, to go to point C, I can first do an orthogonal move upward in an orthogonal direction by n dt, where n is called the lapse function, and then move on the tangential direction by na dt to which point C. So by doing that, my general ds square equal g mu dx dt